Yeah, so I use the library, the mass, for the data set, the Boston. So Boston data set is a pretty popular data set for the real estate data set for in the Boston, and each line that represents the zip code or one block or something. And we have the 504 observations. So if you see, for example, structure of Boston, you can see that we have 506 observations of the 14 variables. And we have several variables. So basically this to try to explain the median home value by some other characteristics. So median home value is the last column, so 24.0, probably 24,000. I think this is an old data set, so numbers are small. You can see the help of Boston to see. Okay, so at first you have to read the library mass, but then you can see the explanation. So help of Boston. Okay, I'm using two screens, so this. So 506 observations for 14 columns. So it's from 1978, so it's old data. So now in Boston, the real estate price is sky high, but at that time, it's much cheaper. And the median home value and other 13 variables, for example, crime per capita, per capita crime rate by town. And this is the, yeah, maybe zone variable, the proportion of residential land zoned for lots over 25,000 square feet. So it's pretty large lot, then probably the home values are higher. Maybe not. Proportion of non-retail business area per town. Yeah, and CHAS, this is the Charles River dummy variable. So the one if the tract bounds river, zero otherwise. So the one thing that some people feel strange is that if the houses are on the riverside or waterfront, then the price is higher. Okay, so it's natural in the United States, but probably in many places near the river is the higher risk for flooding. So probably not necessarily the price is higher in other countries. Yeah, more the crowded cities in maybe the Taiwan or China or some other places. Maybe the distance to the train station is more important to the distance to the water. But okay, so this is important variable, at least in the US real estate market. So probably people are thinking about some scarce locations. So in big cities, the near the train station is the more important factor, and the only limited number of properties that have that feature. But here in the United States, no train stations. So still, some people want to make some premium locations. And NOx, maybe this is environmental variable. So and the room, average number of rooms per dwelling, and the age of the homes, and the distance, weighted mean of distance to 5 the Boston employment centers. Yeah, and the RAD is the index of accessibility to the radial highways. So it's hard to see it's positive or a negative factor. It's more convenient if it's close, but the noise level is higher also. And tax, the full value tax property rate. So tax property rate is lower, though of course it's preferable for the by years. And the pupil teacher ratio by town. So this is also hard to interpret variable. If this is higher, that means it's bad because we have less teachers, but they have less teachers, but also the popular towns have higher the pupil teacher ratio. So the interpretation is not clear. Black, this is the proportion of black by town. This is complicated formula, the 1000 times the proportion minus 0.623 square. I'm not sure why this variable is chosen. Maybe 63% is average in this data set, or I'm not exactly sure. And LSTAT, the lower status of population. So probably it has a negative impact on median value of owner-occupied homes. So these variables are there. So yeah, so now that we want to do the regression, and usually the objective is to predict the median home value, so MEDV. And at first we attach the data set, then linear regression. That is LM, median value, then crime rate. So usually it's good to name this object. So you can directly type it, but in this case, you can just see the intercept and also the coefficient for crime rate. So you can see the higher crime rate means the lower median house value. And crime rate is 0, then 24.0, then crime rate gets higher by 1. That is strange, but if the crime rate is 100%, maybe the number of crimes per population is 100%, then home value is the $0.41 thousand, maybe that's cheaper. Yeah, median home value is in thousand. So that's the case. Yep. And if you want to see the more exact output, you can type the summary, then you can get this. Then also we want to see the confidence interval. For example, you can make a plot of the crime rate and median home value. So this is the scatter plot. Probably linear regression is not optimal because so many observations are concentrated around the zero here. So probably maybe the log of crime rate or something is more appropriate. But anyway, we have some negative relationship between these two variables. So we want to put the straight line here, and also that we want to see how reliable that variable is, that the regression line is. And if you put the AB line of this linear object, then you can see the straight line here. Yeah, another way to put it is just AB line so that you can give A and B. AB line, A is equal to, A is intercept, so the 24.03. And B is equal to negative 0.415, then you can see the same graph. Yeah, this fit is not really good. If we take the logarithm of crime, probably it's better, maybe log of crime or yeah, more normal plot. Still, the median house value, probably this is truncated at 50, so that's why the many observations are at 50. But here, maybe tendency is maybe even clearer. Yeah, but we want to have some confidence band and also the confidence interval and the prediction interval, and also the confidence band and prediction band we want. So okay, so basically, okay, so we go back to the original one, and okay, so we have one straight line, but we want to see how reliable this fit is. So at first, we want to see the the possible area that the regression line that moves around. So you can see that this line, but if the data is different, maybe slope is slightly steeper or slightly smaller, or maybe intercept is slightly larger or slightly smaller. So we have some area that this regression line that goes through moves around. And we can get the 95% confidence interval for that. So that is so-called the confidence band. So that can be obtained by the the predict function. So yeah. So maybe at first, okay. So these are coefficient, and these are intercept, and the coefficient for the crime rate. So we want to see how reliable that these estimates are, and that can be obtained by the conf_int function lm1. And for example, the 99% confidence interval is obtained by here. So the intercept is 24.03, but the 99% confidence interval is from 22.97 to 25.09. And the slope is also here, the -0.415, but the standard error is 0.04. So if we think about 99% confidence interval, so this becomes -0.528 to -0.301. So still, we can say probably the most likely the slope is between -0.5 to and -0.3. So at least negative, some negative value. Yeah, so now that we want to see the confidence band for this regression line, and that can be obtained by predict function. So we name it as CI, predict LM1 interval confidence. The slide is available on the website, so you can download it. And this gives the actually the this value and the upper bound and the lower bound of the area that the regression line goes through with 99% confidence. So if we type head of CI, we have 3 columns, and this is the fit. So if you plug in the crime rate, so crime rate, the first 6 observations are here. So the fitted value is the coefficient using coefficient 24.03 minus 0.415. So this minus 0.415, 19, I think. Then times the 0.00632, then you get the same value as here. Maybe some rounding error here, but in this way that you can get fitted value. And this is the lower bound, and this is the upper bound. So we want to draw the lower bound and upper bound on the graph. And that can be done by the matplot function. So matplot, crime rate, so the x-axis, x coordinate is crime rate, and the y coordinate is house value, but we want to get the fitted value. So yeah, so for now that we just ignore the scatter plot part, and we focus on this line. Of course, we can overlay everything. And if we type CI, we have 3 lines. So this matplot function that draw these 3 lines. We want to make it as the line plot. So type is equal to L, and the color 1, 2, 3. So color 1 is black, and the 2 is red, and the 3 is green in R. And the line type, maybe the fitted value is the center one, so we use 1. And for other 2, lower bound and upper bound, we use the dashed lines. So that is line type 2. So if we type this, then we make this line plot. It's a little bit hard to see. Crime rate. Yeah. Yeah, I said I expected a problematic plot, but actually it's not really problematic. Yeah, so you can see some overlap here. Okay, so probably this part is fine. So this part is fine, but we have some overlap, the strange overlap here. So it looks the same line overlaid several times. So this is because of the order of the observations. So 506 observations are not in increasing order or decreasing order. So it randomly connect these points. So maybe first point is here, second point is here, third point is here, fourth point is here. If it's ordered, it becomes just one beautiful curve. But since order is random, so we have some overlap here. Right, so first one, maybe second one, third one, fourth one, fifth one, sixth one, or something like that. So that's why we can see some multiple lines here. And to correct this, we can order the variable. So we can think about the order of the variable. We define the order of crime rate. So you can see ORD. So first observation is actually the smallest, and the 285th observation is second smallest. So for example, the crime rate of the 1. So this is smallest, and this is second smallest. Sorry, 285. So this is the second smallest, and this is third smallest, and so on. 3, 4, 2. Yeah. So if we think about the order, then you can modify this matrix plot. This the CI object. So we have 3 columns. So this is a matrix. So that we have to just specify the line numbers. So we take all three columns, maybe 1, 2, 3. We can omit this. Then now we can see that just one area. So the regression line that moves between this red curve and the green curve. And this is a little bit harder to see, but actually if we think about the crime rate, the less than 0, that is not possible. But if we think about this graph for x is equal to -100 to +100, actually the band gets wider again on the left-hand side. So it seems that this is widest and this is narrowest, maybe around here narrowest. Then if we continue, it gets wider again. So it's a kind of the hyperbola, and the straight line that moves in between. When straight line randomly moves in terms of intercept and the slope, you can see the range is wider on the right-hand side or left-hand side, right end or left end, because the slight difference in slope makes a large difference in value. And probably it moves but around this point, it doesn't move much. So if slope changes, then still this point does not change. So that's why around here, the band is wide, the narrower. So the range of, so the area that the straight line moves is generally a hyperbola. So we can see that this is not really a straight line. Do you have questions so far? Yeah, we can overlay the plot also, but we have to match this x-axis and y-axis, so we have to be a little careful probably. Scatter plot, climb rate, and the range is maybe 0 to 100 crime rate. That is fine. Then median house value is 0 to 50. So maybe you can say X limit as 0 to 100 and the Y limit as 0 to 50, then we overlay by specifying parameter new is equal to true, then crime rate, then we use the same X coordinate from 0 to 100 and Y coordinate from 0 to 50, probably it makes the overlaid. So in this way, yeah. So this fit is really not good. So probably this isn't really the best way to model the relationship between the crime rate and the house value. But at least we can. Yep.
I'm sorry. Why is the plot capped at 50? What's happening there?
I don't know. This is just the limitation of the data. I don't know why. Because.
Oh, okay.
Yeah, I don't know. Maybe we can see the help. Yeah. Median house value. Yeah, it says nothing about it, but yeah, it sounds it's truncated at 50. Yep. Yeah, so I guess the numbers are pretty large, maybe just a small towns with very expensive houses or something. So that's why they truncated. Yeah, it's not clear. Yeah, $50,000 is pretty cheap. So this is Boston neighborhood. So, but still the 1978. So it's much cheaper. Yeah. And the next one is the prediction interval. So prediction interval is different. So that you can see yeah, this really looks bad. So maybe we take the logarithm scale, then that makes better. So maybe, yeah, maybe LM2. We fit the median house value on the log of crime rate, then maybe, yeah, yeah, predict LM2 plot. Yeah. So now that we think about the prediction interval. So okay, so maybe let me see. Yeah, so plot of log of crime rate. So this ranges from maybe -5, -6, -5, -5 to 5. So the maybe Y limit, maybe 5, maybe 10, 0 to 50. X limit. So L is missing. Yep. So yeah. Okay. So then overlay. Yeah, it looks much better. Okay. So then okay. So the confidence interval. So we put this one. Maybe the log of this and okay, so then X limit, the -5 to 5 and Y limit and 0 to 50. Okay. Okay, so I have to overlay it. So parameter new is equal to true and matrix plot here. Okay. So this is the range that the line moves around. So this is pretty narrow range. So the regression line moves it, but moves here. But the observations have much wider range because that has some error. Okay, so think about the y is equal to a plus bx plus epsilon. then straight line is just y is equal to a plus bx. Don't consider epsilon. So that's why the observations are not within this range. So this is just the regression line, the area that regression line moves. So now that we want to see where the observations, so expected the area that the 95% or 99% of observations exist. So that is called the prediction interval, and that it can be done by very similar code by using this predict function with the predict option. So we pi interval predict. Okay. Yeah. So now that we want to put this prediction option, so that we put parameter new is equal to true, and the matrix plot, we do the same thing, but this time that we use the pi. Then we get this. So this is the range that 95% of observations move around. So yeah, it's a little bit strange because we have the more observations here and less observations here, but you can see the approximately the 95% of observations are within this range for maybe if the more observations are available. And you can see we have 506 observations, and 95% of it is 25. And if you count the number of observations out of this range, we have one observation here, then we have maybe the 8, 10, 15, 16, and maybe the 21 and the 25 and maybe 31 observation out of the range. That is about 5%, right? So the about 95% of observations are within this range. Yeah, so this consider the error term, epsilon term also. So for prediction, that we use prediction interval, and if we want to see the regression line, we should use the confidence interval. Straight line is within this range if data changes, and the observations are within this wider range. That is the prediction interval. So these are useful graphical expression of the regression. Yep. And now we think about the which observations are more influential, higher leverage. Then 381st observation is the largest, has the largest HAT value, that is the largest leverage. Or if you want to see the several, larger values, then HAT values then we have 506 observations. So the largest three, the HAT values, largest three leverages are given by 406 observation and 419th observation and 381st observation.
I'm sorry, I'm still a little confused on the HAT values. So is that the largest error in the regression? Like these are the outliers, or what does that mean?
Basically, this means the observations are far away from the center in terms of predictor values.
Would that mean they're the largest residuals then? Is that the right way to say it?
Not really. So if we see here, probably so this observation, maybe this observation, and maybe this observation and this observation. So these are the observations with the highest leverages. So in terms of x values, it's far away. So that the straight line is affected a lot by those observations. Actually, these are not outliers here, but if this observation, for example, this observation is around here, then it has much higher influence to this regression line, right? If this observation moves here, then maybe the regression line is much steeper. And if observations are around here, maybe this line becomes almost flat. So one observation on the left-hand side, left end or right end, so it has much higher influence. So
okay, thank you very much.
yeah, sure. And then we use some package, the library map_tools to identify which observations are 381st observations and so on. So then, okay, so again, the plot the crime rate, maybe the log of crime rate and the median home value. And the point level, so that we have now this one. And the point level of the x is equal to the crime rate. Maybe I should say the log of crime rate. And max, oh, sorry. So we get the 3 largest one. So we name this 3 observations. So maybe max 3. Then point level. So we want to see where these 3 observations are. So log of crime rate, max 3, and the y is the median value of this max 3. Yes. So max 3 is just these 3 observations. So just we pick up these 3 observations. Then we can see where it is. And to put the labels that we should point label function is not found because probably library is not. Oh, okay. So this is library. R is missing, so that's why. Library. Point label. I think around here we should get the R. It doesn't work well. Library. I think some problem about the loading some package. Sorry, I cannot reproduce my result in the chapter 3 slides. But if the package that works well, then you can see the 3 observations around here. So this is actually the before taking logarithm of crime rate. But I think that these numbers are the same. So hat values still given by the same observations. So these 3 observations are most influential to determine the regression line. Yeah, obviously before taking logarithm, that these observations are farther away from the center of the crime rate. So that you can see that these observations are most influential to determine the regression line. Sorry, I don't know why it does not work. Oh, maybe. Levels, median, mid V, maybe. Yeah, it now works. So these 3 observations are most influential to determine the regression line. So probably the center of the log of crime rate is around here. So actually these observations have less influence and these observations have more influence. So these observations are more influential to determine the regression line. So if this observation moves, then probably the slope of this regression line, the change is more. So average, the log crime rate is negative 0.78. So that is around here. So probably the distance is larger for these observations compared to maybe these observations. Yeah. So next, we think about the analysis of variance. So we have just one variable, the log of crime rate, to explain the median house value. But what if we use other variables? Maybe we can see the crime rate against, the home price against maybe the distance from the city center. There's still some positive relationship. So if we add this variable, maybe it improves the model. Or NOx. Actually, if environment is good, the air quality is bad, actually the median house value is lower. Maybe in the suburb, maybe price is higher, maybe in this data set. So think about introducing these two variables in the linear model. So we define the LM3 as LM, median value, on crime rate, log of crime rate, and the distance from the city center, and NOx. Then we can see this. So the log of crime rate still have the significant coefficient, but also the distance from city center and NOx level are very significant predictors also. So probably this model is better than the previous model. Maybe we can see the previous model again. Previous model, the adjusted R square is 20.48%, 20.5%. And here the 24%, 24.1%. So it's slightly better. But of course, we have more variables. So it's natural that the model is better. So we want to see if this is significantly better than before. So we can do ANOVA of LM2, LM3. So we can compare if we can test if additional variables are useful. And actually, we add two predictors, and this is very significant because this F value is 13, and the P value is much less than 0.05. So you can see, so these two predictors works well to improve the model performance. Yeah, also you can think the AIC value. So AIC improves by 22, only two variables and 22 improvement. So that is pretty good. So if variable is useless, then one additional variable makes AIC worse by 2, so larger by 2. But now it's smaller by 22. So we can say that the two variables are really useful to improve the model. Yep. So this is chapter 3. Lab session. So now probably that you are comfortable to deal with linear regression in R. Okay. Any questions on R code or linear regression in general? So in R, we have the several graphic function. So one graphic function gives everything. For example, the plot XY, then we can make a scatter plot. And some additional functions are available. For example, AB line. AB line add something on this plot. But sometimes if we want to overlay two plots, actually you have to really generate the two plot, and you have to make them overlaid. So that is a bit a hassle. Plot something and parameter new is equal to true, then another plot. But we have to be consistent about the name of the x-axis and the name of the y-axis, and maybe scale of x, scale of y, and so on. Yeah. So pairs function makes all pairwise plot for these observations. Actually, we have 14 variables, so maybe there are too many variables. That's if you just restrict this to maybe median house value and the NOx level and distance from the city center, crime level, so then we can see the graph more useful, maybe the 5th and 8th, maybe. So if we only pick up the first column, 5th, 8th, 14th column, so you can see scatter plot of median house value and distance from city center, NOx, and the crime rate. So previously we have seen this graph and this graph and this graph. We have negative relationship, positive relationship, and so on. The correlation coefficient is also calculated by COR function. So you can see correlation coefficient, the crime rate and the median house value, negative 3.88. NOx level, negative 0.42. Distance from the city center, 0.24. So actually, the farther away from the city center, the house value is higher. So probably the suburb has higher house values. Yeah. Okay, so if you don't have questions, then we go on to chapter 4. Yeah, really, the linear regression does a lot of analysis. So even you join some data competition, such as Kaggle, maybe the first you try linear regression. Usually the performance is the bottom 10% if you only use linear regression and optimize the predictors. Still, you will beat the 10%. Probably those 10% are made by some computational errors or some coding errors. But at least that is usually the start line of the prediction model. Yeah, so Boston dataset, in the past, before I developed this course, the students compete each other to predict this dataset better. So I have a bunch of the performance on the prediction performance on this dataset. So if you use some cutting edge method to predict the median house value of this dataset, you can report the cross-validated the error size, the root mean square error, then I can provide the whether or not it's good. Okay, so now that we go to chapter 4, and maybe I'm using iPad to share the slides. So chapter 4 slides are available on the website also. I don't know why it does not work. Okay, probably now it's good. Okay, so have you studied logistic regression? So in 5030 or 6840, there you have studied the logistic regression, but I don't know, the Objet. Anyone took the Objet's 5030?
I did. We covered it a little bit.
Oh, covered a little bit. Okay, great. Then that should be fine. And 5800 usually does not cover logistic regression. So yeah, if you have already known that this is just a review, but otherwise you can just listen carefully, then yeah, you can see it. Okay, so the chapter 4 is classification. So the y value is categorical. So x, maybe we have multiple variables x1 and x2. And the x1 value and the x2 values, then y values. But the y values, we only have the categories, maybe ABC or something. So categorical. So we have several models. The first one, logistic regression, and the other ones, the linear discriminant analysis and the quadratic discriminant analysis, and also k-nearest neighbors. And the logistic regression is basically for two categories. So when k is equal, k is the number of categories. K is equal to 2. And actually, there's some extensions to allow the k is equal to 3 and more, but it's a little bit more complicated. So this is called the multinomial logistic regression. That may have been covered in 6840. And the linear discriminant analysis and the quadratic discriminant analysis. So this is for any k. So the idea is that we think about the center and that we, what should I say? So linear discriminant analysis, we think about just the center of each group. So maybe the linear discriminant analysis. So we have labels, so 3 groups, group A, group B, group C. And we think about a kind of the center of the data. So center is here, and the center is here, and the center is here. Then we think about the distance from the center. Then that we classify observations, classify any point on the plane by the distance from these 3 centers. Then you can see the probably, okay, so you can divide this area by this line. So you can connect these 2 centers. Then we think about just the midpoint of this. Then we can do this for all pair of observations. Then you can see this is area A, area B, area C. And you can divide the entire space of predictors. Sorry, that this is x1 and x2. Entire area into the 3 pieces or 4 pieces and so on. And linear discriminant analysis, this boundary is linear. And the quadratic discriminant analysis, the boundary is the quadratic curve, such as the parabola or hyperbola. And the k-nearest neighbors, we have covered in chapter 1. So just think about the closest k observations. Maybe k is different from this k. Maybe I should say maybe G here. So k-nearest neighbors is that we choose closest k observations. For example, closest 5 observations. If we have new observation here, then closest 5 observations are these 5. So everything is the crosses. So it belongs to group. This point belongs to group A. So it doesn't have much theory behind it, but we cover this in lab session only. So we do computer implementation only. So today's topic is just logistic regression. Yeah. Okay, so but before that, the overview. So examples of classification. So classification is useful in many places. So one is maybe the categorized handwritten digits into classes 0 to 9. So typically we have a sample data set with maybe the 1,000 handwritten digits. Then based on that, we create the model that to read other maybe millions of the digits. Yeah, and the more classic example, categorize 150 flowers into 3 species based on the measurements, such as flowers diameter. Yeah, or the simpler one. So this is, okay, so G is equal to 10. This is G is equal to 3. And the last one, only 2 classes. Judge whether or not patients are malignant based on several medical measurements. So malignant and benign, we only have 2 categories. So here 3 species. So this is the malignant and benign. So we only have 2 classes. And the first one, we have 10 classes. Yeah, so this is an example for the categorization problem with G is equal to 2 groups. And this is balance and income of the individuals. And this blue means not in blue is not in default and red is in default. So if the income is lower and the balance is higher, then we have more default. And in the other case, then we have less default. But actually, it seems the balance is more dominant factor to determine whether or not people default. So this is basically X sub 1 and this is X sub 2. And this label is Y, blue or red. And you can see the balance is really a good factor to predict the default. Income does not really predict the default. So at first, this kind of scatter plot or box plot is useful. But the box plot only see the marginal distribution, and the scatter plot can only see 2 predictors, up to 2 predictors. So in general, we have more predictors. So statistical model that helps you to understand the situation. And for why we cannot use linear regression. So almost the reason is clear. So at first, if we have the more than 2 categories, maybe we have 2 categories, then we can still make 1 as one group and 0 as the other group. But if we have 3 categories, we have the more problems. So for example, if we predict the blood type by some other body measurements, then how to align A, B, O, and AB? So that is not really clear. So that's why we cannot use linear regression. And yeah. So even if we have the order in categories, for example, the movie rating from 0 to 5, 1 to 5, sorry. Then 1, 2, 3, 4, 5. So of course, 2 is better than 1, and 3 is better than 2. So we have order, but we are not sure whether this distance is equal to this distance. Maybe the rating of 1 is much worse than 2, but the 2 and 3 are very similar. That's possible. So just no justification to regard these intervals equal. So that's one problem. And also even binary classification problem that we can see, the fitting a straight line that usually isn't a good idea. So this is, okay, so X predictor, and this is Y, and the default or not default. So this is the not default, not in default. And this is default observation. And these yellow points, we have many points here and more scarce here. And we have many points here, some points around here. Then fitting a straight line that doesn't make much sense. So we can still it is maybe better than nothing, but if we fit straight line, it's really hard to interpret. So because the value is either 0 or 1, so how to interpret this, the 0.2 or something? Or what happens around here? So the fitted value is less than 0. So it does not make much sense. So it's not good. So basic idea is that since all points are on this line, y is equal to 1 or y is equal to 0, that we fit this kind of line to predict the probability that y is equal to 1. So you can see, for example, around here, more observations are 1. And around here, more observations are 0. So that means around here, balance is 800, then probability of default is very close to 0. But around here, probability maybe 2000, the probability of default is higher, maybe 70% or something. So basically we consider this nonlinear regression. So so we wanna fit this kind of curve for this binary data. Yeah, so now that we do the logistic regression, so the two categories, so G is equal to two categories. More than three or more, that we cannot see. There is no way to make it the numeric variable in an objective way. So think about just G is equal to 2, then the class is either 0 or 1. Then still we can do some regression. And suppose that the response variables is a 0 or 1, and x is a predictor variable, which may be quantitative or qualitative. Then we think about probability of y is equal to 1 given x. So given balance, what's the probability that the person will default within 3 months or something like that? So the x is larger, the default probability is higher. So that we say that as P of x. And we assume the probability is in between 0 and 1. So never 0 or never 1, or never exceeds 1 or never below 0. So this is probability. So it's possible that the probability is 99.9%, but not 100%. Just it's within the open interval 0, 1. And the logistic regression assumes that the probability of y is equal to 1 is represented by f of beta naught plus beta 1 x. So here, the beta naught and the beta 1 are parameters. And f is a fixed function, deterministic function. And the f of a is the e to the power a over 1 plus e to the power a. So you can see that a is very large, a goes to infinity, then f of a goes to 1. And a goes to negative infinity, e to the power a that goes to 0. So 0 over 1 plus 0 is 0. So f a goes to 0. And f is called logistic function. And yeah. And f is a function from r to 0, 1. So you can see a goes to infinity, then fa goes to 1. And a goes to negative infinity, fa goes to 0. And this is monotone function. Yeah, so this means that p of x is explained by a linear function of x. But since p of x should be between 0 and 1, we have the function f. And this is the function f. So this is the y is equal to the e to the power x over 1 plus e to the power x. X is equal to 0, the value is 0.5. And this goes to 1, this goes to 0. Yeah, so now that we think about some example. So this is the data set with 10,000 observations, the default data set, and the X1 is balance, X2 is income, and the default status, this is the Y. So this is Y. So this is no or yes. We only have two values, X1, X2, possibly the indicator variable for student, maybe X3. Yeah, so if we think about the balance that we can see this data, so observations are concentrated in 0 or 1. So this is not in default. And this is default. Then now that we want to fit this line. So basically this the blue line. Remember that this blue line is f of, so this one, okay, so this is y, this is x, then y is equal to f of beta naught plus beta 1x. So that is equal to the e to the power beta naught plus beta 1x over 1 plus e to the power beta naught plus beta 1x. So once beta naught and beta 1x is determined, then this curve is determined. So we want to determine this, the beta naught and beta 1. Okay, so that this is px, so we want to determine the beta naught and the beta 1. And the next we will discuss how to estimate this beta naught and the beta 1. But for now, actually we have some discussion about this functional form. So this one can be translated into this. Okay, so yeah, you can see that the 1 minus p of x is the 1 minus this quantity. So that becomes 1 over 1 plus e to the power beta naught plus beta 1x. Right? So if you take the ratio, the denominator cancels, and this just becomes e to the power beta naught plus beta 1x. Then take logarithm, then we get this. So the logistic function is complicated, but you can interpret this as the ratio of success and failure. This is the probability of success. And this denominator is probability of failure. Log of this, the ratio of probability, that is linear function of x. So we can interpret in this way. So the left-hand side is called the log odds. And also it's called the inverse logistic function of x. I think that sometimes the logit link or logistic link is this inverse logit function. So that always I mixed up the logistic function and inverse logistic function. And when we say logistic function, that is the e to the power x over 1 plus e to the power x. But when we say logistic link, I think sometimes the wording is the other way around. But anyway, so this is the inverse function of the logistic function. Okay, so now that we want to discuss how to estimate the beta naught and the beta 1. And remember that the linear regression, the estimation is really good. I mean, based on more beautiful theory, because to estimate beta naught and beta 1 in linear regression, just we minimize the sum of squared errors. We have y sub I, x sub I, epsilon sub I, then we minimize summation of yi minus beta naught minus beta 1 xi. So we minimize sum of epsilon I square. So that is the sum of the yi minus this. And this is quadratic function of beta naught and beta 1. So it's easy to estimate because the quadratic function is parabola. So if we think about beta naught and beta 1, and this is the function, so this function, so this is suppose the g of beta naught and beta 1, then this is the z is equal to g of beta naught and beta 1. Then this is parabola, so we can easily find this, the minimizer of the function. But logistic function, that we cannot do the same thing because we only have probability here. We don't have error term, so we cannot minimize the sum of error terms. And also this function is very complicated, so it does not work as simple as linear regression. So we use maximum likelihood method. So that means that we maximize likelihood by optimize beta naught and beta 1. So here's the notion of maximum likelihood. Yeah, I think that 5800 covers maximum likelihood, and 5030 also covered it, I believe. So just briefly, I do that. And consider the situation. So what is the maximum likelihood? So consider the situation to randomly pick up a die out of 3 unfair dice, X, Y, and Z. And that we roll the die once. And suppose that you don't know which die you use, but you can observe the result. And suppose that you pick up either X, Y, or Z, and the result is 2. These 3 dice have different probability. Die X is actually the fair die, so probability is 1/6 each. And die Y is a loaded die. It's more likely to have 1, but the same probability to 2 to 6, and the probability is 1/10. Die Z, that we have higher probability for the 2, and also higher probability for 1, and much lower probability for 3 to 6. If you observe one result, the face of 2 faces up, then which die most likely you rolled? Then the idea is compare these 3 vertically. Then you compare these probabilities. Then which is the largest? So you can see the die Z have the largest probability of the having 2. So our maximum likelihood estimate is Z. So that is the maximum likelihood method. So when you study probability theory, we only see this as, we only interpret this for each line. So each line is a probability space. So die X gives a probability space, die Y gives probability space, die Z gives probability space. But here, maximum likelihood method see this graph vertically. So we focus on the column, then we compare these numbers and see which is the largest. So that is the concept of the maximum likelihood. So to be exact, what to do, how to do maximum likelihood for logistic regression. So here is the way. Okay, so suppose we observe x1, y1 to xn, yn observations. And the likelihood is given by this. Probability of xi given yi. So maybe to be exact. So suppose we have the xi and yi. Okay, so yi is the 0, 1, 0, 1, and the x is maybe 1.5, 2.5, and 1.0, and maybe 1.4 or something. Then we have the P of x1. P of x1 is probability of y is equal to 1, right? So probability of y1 is equal to 1 given xi. Okay. And if xi is 2.5 and the yi is 1, then the likelihood is the P of 2.5, right? Because P of 2.5 is probability of yi is equal to 1. And actually yi is equal to 1. So this is the likelihood. And if yi is equal to 0, then likelihood is 1 minus the P of 1.5. Right? For example, suppose the P of 1.5 is 0.7. So that means that our predicted success probability, our probability, the predicted probability of yi is equal to 1 is 70%. But actually it does not happen because y is equal to 0. So that means our likelihood is 30%. So that we multiply that for all observations. So that we multiply this number times this number times the 1 minus the probability of 1.0 times the probability of 1.4. So this is the likelihood. And in general, if we have n observations, the likelihood is written as this. If yi is equal to 1, we multiply the p of xi. And if yi is equal to 0, we multiply 1 minus the p of xi or my xj. Yeah. Yeah, so if predicted probability is 80% and actually it happens, then it's correct in some sense, 0.8 correct. And if predicted probability of y is equal to 1 is 0.8, but actually yi is equal to 0, then it's not successful. Actually, the 20% occurs. So likelihood is 0.2. So we multiply this. So this is the likelihood, our likelihood function. And if we write down this, the p of xi is this term, and 1 minus p of xj is this term. So basically, we have to maximize this quantity by optimizing the beta naught and beta 1. So basically, we maximize this function with respect to beta naught and beta 1. And that cannot be done simply, but we have to use some computational method. We have to use the numerical method to optimize it. But actually, this is a convex function of beta naught and beta 1. So we have the pretty good approximation. So if, for example, we use the Newton-Raphson method, then the likelihood increases when we update beta naught and beta 1. So optimization isn't as difficult as it looks. So it's not parabola, but still this is the convex function. So the proof is in the textbook, The Elements of Statistical Learning. So the textbook, so this book is in the syllabus so that you can see, I think in chapter 4 also. Then you can see the proof that the likelihood function is convex. And if we estimate in our language, that we can get this. So the default probability is negative 10.65 plus 0.005 times balance. And we use f. So f of x is equal to e to the power x over 1 plus e to the power x. So if you plug in numbers, then you can calculate the default probability. Yeah, actually, sometimes it's simpler to write this as 1 over 1 plus e to the power negative x. Yeah, again here, this book has more details. And if you want to calculate predicted probability, so given x, what's the default probability? When the balance is $2,500, what's the probability of default? Then you can just plug in beta naught hat and beta 1 hat in the original equation, and you plug in the new value of x naught. If balance is 2,500, they plug in 2,500, then you can have the predicted probability of default. For example, our estimates are here. So if balance is $1,000, then you plug in $1,000 here, then you get the 0.00576. So balance is $1,000, then the default probability of that person is only the 0.576%. So it's pretty low. Yeah, if X has qualitative predictor, you can use the dummy variable, so indicator variable for that category. So the logistic regression works in the same way.